Good morning, everyone, and welcome to today's laboratory session. As postgraduate psychology students, you are already well aware that human memory is an incredibly complex architecture. But today, we're going to step away from traditional storage models and look at memory through a much more analytical lens. We'll be conducting Experiment 2, and our primary objective here is to rigorously examine Craik and Lockhart's highly influential levels of processing theory. Basically, we want to figure out exactly how the depth of cognitive processing directly influences memory performance and long-term retention. To do that, our academic agenda today will follow a logical progression. We'll start with the theoretical background and principles, then move into the laboratory experiment design. After that, we'll cover the experimental procedure and execution, followed by observation and data analysis. Finally, we'll dive into the cognitive interpretation and mechanisms, and wrap up with applications and your Viva evaluation. Section 1. Theoretical Background and Principles. Let's first ground ourselves in the theoretical framework that's going to dictate today's experimental observations. You see, the objective of this practical is to really understand the mechanisms behind memory, rather than just passively recording observations. We need to shift our focus away from where memory is stored to the actual quality of the cognitive processing itself. This framework, proposed by Craik and Lockhart back in 1972, essentially argues that memory isn't just a collection of separate physical stores, like short-term or long-term boxes in the brain. Instead, memory is a direct consequence of the quality of processing applied to incoming information. Information that only gets superficial attention is forgotten quickly, whereas information processed for meaning is retained for much longer. Successful learning is all about meaningful cognitive activity, not just mindless repetition. Now, this theory proposes three major levels of processing that incoming information can be subjected to. As you can see on this chart, as we move from left to right, the depth of encoding increases. First, we have structural processing, which involves very shallow physical analysis. Here, attention is directed strictly toward physical characteristics, things like capital letters, font, color, or the length of a word. Because there's very little actual meaning being analyzed, memory retention here is usually pretty poor. Moving a bit deeper, we hit phonemic processing, which relies on sound. This is where learners determine whether words rhyme or sound alike. This produces better memory than structural processing, but it's still considered relatively shallow. Finally, we reach semantic processing. This requires deep, meaningful cognitive effort. You're connecting new data to existing knowledge, personal experiences, and broader concepts. This deepest level is what produces the absolute strongest and most durable memories. Section 2. Laboratory Experiment Design. Let's outline the precise methodology and design required to actually test this psychological principle in our lab today. Our aim is to empirically study the effect of these different processing levels, operating on the principle that processing depth determines memory durability. For this practical, you're going to need some standard laboratory materials. Make sure you have your standardized word lists, response sheets, pens or pencils, a stopwatch for precise experimental control, and a scoring sheet to objectively record your data. To maintain scientific validity, we have to strictly isolate our independent variable, which is the level of processing, structural, phonemic, or semantic. We'll then measure its effect on our dependent variable, the exact number of words correctly recalled. But crucially, you must meticulously standardize your controlled variables, the number of words, the presentation time per word, the testing conditions, the exact instructions you give, and the recall interval. All of these must remain completely identical across all conditions. That is how we ensure our results are purely a product of cognitive depth. Section 3, Experimental Procedure and Execution. Let's walk through exactly how you'll administer this to your participants. Pay close attention to these steps. First, you'll present the word list one at a time, but make sure you do not reveal the expected outcome. Then, you'll sequentially assign the different processing tasks. Once those tasks are complete, you'll drop the surprise, administer an unexpected recall test. We do this to prevent any intentional memorization strategies from your participants. Finally, you'll objectively record and compare the correctly remembered words under each condition so we can mathematically analyze the recall rates. As postgraduate psychology students, I want you to observe this setup carefully. Notice how the structural task only requires subjects to analyze physical traits, like fonts or capital letters, but the semantic task
That forces them to process the actual meaning. You might ask them to judge the meaning or creatively relate the word to a sentence or a personal experience. It's a brilliant way to force the participants' cognitive architecture to engage at distinctly different depths.
Section 4. Observation and data analysis. Once your procedure is complete, we transition to data collection and empirical observation. Let's look at what we expect to find. Notice how the depth of processing dramatically influences recall on this chart. If you've controlled your variables correctly, your data should mirror this exactly. Structural processing yields the lowest retention, represented by that lowest bar. Words processed phonemically show moderate recall. But look at the semantic processing. It generates a highly superior recall rate, towering over the other conditions. This empirical data is literally the physical manifestation of cognitive depth. Section 5. Cognitive interpretation and mechanisms. Now, we have to act as cognitive psychologists and interpret why these statistical differences exist in the first place. I want you to think critically about this question. Why exactly does semantic processing produce such superior long-term retention compared to shallow processing? Don't just accept the graph at face value. What is happening in that awe-inspiring, intricate information flow of the human brain? Well, it comes down to the fact that meaningful encoding fundamentally strengthens memory traces. Deep semantic processing actively integrates new information into established semantic networks, which creates incredibly robust retrieval pathways. You're connecting data to existing knowledge and concepts. On the flip side, shallow processing, like our structural condition, relies on simple exposure. It completely lacks this intricate integration, so it only produces weak, transient memory traces that degrade rapidly. Section 6. Applications and Viva evaluation. Finally, let's examine the practical utility of this cognitive architecture and get you ready for your laboratory evaluation. Beyond the walls of this laboratory, this framework has massive real-world implications. In educational psychology, it promotes active learning and concept-based teaching, effectively discouraging old-school rote memorization. It proves that helping students prepare for exams requires strategies that force semantic engagement. Just rereading text simply isn't enough. Clinically, it's absolutely crucial. This theory directly informs how we design memory training, how we conduct neuropsychological assessments, and how we develop cognitive rehabilitation protocols for patients. So, the major conclusion you need to take away from this practical is that successful learning is inextricably linked to meaningful cognitive activity. The quality of cognitive processing, rather than simple repetition, determines how well information is remembered, making semantic processing vastly superior for long-term retention. This single conclusion is what makes Craik and Lockhart's theory one of the most influential explanations of human memory. I'm going to leave you with these 5 viva voce questions. I expect you to analyze these independently as you finalize your laboratory reports. Reflect deeply on the cognitive mechanisms responsible for your observations, why that recall test absolutely must be unexpected, and how you'd apply these theoretical findings in a real neuropsychological assessment. Thank you for your attention to detail today, and I really look forward to reviewing your empirical findings. Let's get to work.